Okay, so welcome back to the second part of the video on L-infinity and why it's not a separable metric space. Okay, so I was just describing the infinity metric on L-infinity, and we said that it was the supremum of the modulus of xi minus yi, where you vary I over all natural numbers, which is equivalent to writing the supremum of the modulus of x1 minus y1, and then you've got the modulus of x2 minus y2, all of these elements, all of these terms, the modulus of all of these terms in a set together. Take the supremum of that, and I was just posing the question why this supremum exists. And the reason it exists is because x and y are elements of L-infinity. If they weren't elements of L-infinity, it wouldn't be guaranteed that it exists, of course. But because they are elements of L-infinity, it implies that the supremum over I is an element of the natural numbers of the modulus of xi is some finite value, because if we go back to this definition, if x is an element, this is precisely the definition. It had to be some finite value. So let's call that value mx, shall we? Mx. And similarly, the same holds for y, that the supremum of the modulus of all of the terms in the sequence y, so over all I is an element of the natural number, has to be equal to some finite value which we'll call my, okay? So this implies that for all terms in the sequence, so for all, and let me just put a proper imply sign, for all I is an element of the natural numbers, the modulus of xi is less than or equal to mx. That's just the definition of mx being an upper bound. Similarly, for all I over here, modulus of yi is less than or equal to my. We also know that the modulus of a plus b, whether you're talking about the real numbers or the complex numbers, it's true that the modulus of a plus b is less than or equal to the modulus of a plus the modulus of b. So, if we consider xi minus yi, that's basically equivalent. What we're going to do is we're going to consider a as being xi, and we're going to consider b as being negative yi. So what we're going to consider this as is we're going to imagine putting a plus sign in the middle there and having plus minus yi, basically. And we're going to consider minus yi as the sequence b. Okay, and what we also have to make sure, what you need to note is that if the sequence y is an element of L-infinity, then the sequence negative y is also going to be an element of L-infinity, because where the condition involves this modulus. So if you take all the terms and make them negative, i.e. you take the negative of the sequence, then the modulus, all these terms, their modulus isn't going to change. So this supremum will still be finite, even if you take negative signs in front of all of these. So if x is an element of L-infinity, then negative x is also an element of L-infinity. Okay, so this is perfectly valid, basically. So what we're going to do is then just apply this inequality and say that this is less than or equal to the modulus of xi plus the modulus of negative yi. And then what we do is we note, as I just said, that the modulus of the negative yi is just the same as the modulus of yi. So this becomes less than or equal to the modulus of xi plus the modulus of yi. But we know that the modulus of xi is less than or equal to mx, and the modulus of yi is less than or equal to my. Now, if you put these two things together, those two imply that the modulus of xi plus the modulus of yi is less than or equal to mx plus my. So then by transitivity, what we have is this thing here, which is, if I just rewrite it because it doesn't look awfully clear, it's modulus of xi minus yi. We know that that is less than or equal to, so if I box that, that is less than or equal to this thing over here. So I'll get my pen, this thing here. And this thing here is also seen over here. So by transitivity, if this is less than or equal to this, and this is less than or equal to this, then it implies that this one is less than or equal to this one. So we get that the modulus of xi minus yi is less than or equal to mx plus my for all I as an element of the natural number. So that's how we know that this supremum exists at all. Okay, so we've shown in previous videos that this is indeed a metric space. So if you go back up the playlist, you'll be able to find a whole video on L-infinity being a metric space, and we check all the conditions. We're not going to go through that again. Instead, what we're going to move on to is the separability criterion. Okay, so remember that a metric space is separable if you can find a countable subset of that metric space, which it is a dense within that metric space. So okay, so what we want to show is that there will be no such countable subset in L-infinity, and if we can do that, then we've proven that L-infinity is not separable. And basically the way we're going to do it is by looking at a specific subset of L-infinity. So I want to introduce you to a subset of L-infinity, a very special subset of L-infinity. Okay, so this is the subset of L-infinity we're going to consider. We're going to consider all sequences. So let's call this set T. This is going to be the set of all sequences X, so let's say X is equal to X1, X2, X3, etc. But the terms have a very specific bound on them. Xi's can only be equal to either 0 or 1, so they are all either 0 or 1. Okay, and that's the condition on them. So it's basically all sequences which are just made up of infinite sequences of zeros or ones. So we have, this is an example, 0, 1, 1, 0, 1, 1, 1, 1, 0, how long do I have to go on for? Basically, or you can put them in whatever order you want. All you have to do is just tell me for each term whether it's a 0 or 1, and you can have whatever you want there. Okay, so this is a subset of L-infinity firstly, is what I want to convince you of. So T is indeed a subset of L-infinity. It's a proper subset, it doesn't include the whole thing. For instance, L-infinity, I can easily give you a sequence that isn't in here. So just take the sequence 5, 0, 0, 0, and 0 forever or more. That's a sequence in L-infinity because it satisfies the condition that the supremum of all of its, the modulus of all of its terms is, well, it's 5. So it's finite, so that is certainly an element of L-infinity that's not an element of here. So it is a proper subset of L-infinity, and the reason it is a subset of L-infinity, the reason all these sequences are in L-infinity is that remember the criterion to be in L-infinity is that the supremum of all the supremum of all the terms in the sequence, I as an element of the natural number of the modulus of all the terms, has to be finite. Well, all these terms are either 0 or 1, so the supremum is either 1 if you have a single 1 in here, or it's 0 if your entire sequence is just 0, 0, 0, 0, 0, 0. So it's certainly finite, basically, because it can only be 1 or 0. Okay, so all those sequences are in L-infinity, so T is indeed a proper subset of L-infinity. Okay, now what I want to convince you of is that T is an uncountable set, so it's not a countable subset. Okay, so let's convince you that T is uncountable. Okay, so the way that we do this is using a clever trick. This is in fact a binary expansion of a real number. We can consider it a binary expansion of a real number. So for instance, if you take the interval between 0 and 1, so this is the interval between 0 and 1, and basically the way we're going to specify each real number is if you take a real number x, so let's say this is our real number x, well the first thing you do is you split the interval in half, you split it into a half, and then basically we're going to describe x by a sequence, and the way you're going to do it is if it's in this bottom half here, the first element of the sequence would be 0, and if it's in the top half, i.e. the interval from half to 1, then the first term of the sequence would be a 1, so you put a 1 here for this x here because it's in the top half. Then what you do is you split up the next interval that it's in again, so you split this up here. Indeed, obviously, if it was in here, you'd split it up down here. But now, because it's just in here, we're only concerned with this interval. So what you do is you then split it up again, and it's either in the top half or the bottom half. In this case, I drew the drew the division to the right, so it's in the bottom half, so we describe it as 0 for the second term because it's in the bottom half rather than the top half. If it was in the top half, we describe it as 1, and you go on and on and on and on, so you keep splitting up the interval it's in and giving you either a 0 or a 1. So that is the notion of a binary expansion of the real numbers. And the way you go from a binary expansion back to a real number, this is the way you go from a real number in the interval 0, 1 to a binary expansion. The way you go back from a binary expansion to a real number is that you take, let's call this binary expansion this sequence x, the way you do it is you take the sum of xi, and you need to, if it's a 1, you need to add on, so I'm just going to write it out and then explain why it's true. So xi times a half to the power of I, basically, is the way you do this. Is that right? Yes, I is equal to 1 to infinity. If you take that sum, I think that will take you back to the real number. So basically, you sum up the series, which is made up of this sequence. So this is the series x1. So for I is equal to 1, we get x1, a half to the power of 1, so over 2, plus x2 over a quarter, plus x3 over an eighth, etc. And the reason that that works is if we draw the picture again, down here, if you were in the top half, you got a 1, so that meant you were past a half. So if your first number was a 1, then we're adding on a half basically there. So you've got that half already, okay? So now if you were in the bottom half, with your first element was a 0, so you start off down here, which is correct. You don't want to add on a half if you were down here. Okay, then what we did is we divided up the next bit for either case, whichever one you were in, whether you were in the top or the bottom. We divided it up again into a half, and then if you were in the bottom bit, you got a 0, and if you were in the top bit, you got a 1. And basically, each time it's going to add on the bit, this bit, and it's going to converge up to whatever you wanted. I hope that that is clear why this series is going to converge on your real number. It's because these x1s and x2s and x3s were exactly chosen so that this series was going to converge. Because if you were past this half, you needed to add on the half, whereas if you weren't past the half, you didn't need to add on the half, so that's why we put a 0 there. And again, if you were past a quarter, you needed to add on the quarter, and if you weren't past the quarter, you didn't need to add on the quarter, etc, etc, etc. So this is the way you go back from a binary expansion to a real number. So basically, all of these sequences in this set T are binary expansions of real numbers. So basically, with this function here, with this mapping, I can map all of these sequences onto a real number in the interval 0, 1, and equivalently it's a 1-to-1 map because it's got an inverse here where you can go from any real number to a binary expansion. So they're in bijection basically. So I have a bijection between this set and the real numbers, so that exists f, which is mapping T onto the interval 0 to 1. Now this set is uncountable, so this is uncountable. It's famously uncountable. Uncountable. So the fact that we have this bijection, and sometimes bijections are emphasized by putting a curly thing there and a double thing there, a double arrow there. The double arrow represents that it's a surjective, and this curly bit back here represents that it's injective. Okay, so both of them together represents that it's bijective. Okay, so we have this bijection, which implies that this is also uncountable. So we have an uncountable set here. Uncountable. Okay, so now we note some more properties of this set T. It consists of all sequences of this form where you have just zeros and ones, and we can ask, what is the distance between two distinct members of this set? So remember, let me just write out the set again. It's all sequences where the elements of the sequences, the terms, are either 0 or 1. So all of these terms, xi, is equal to 0 or 1. And these sequences, by the way, I should have mentioned this, because remember, L-infinity, I didn't say to you whether it was going to be a complex L infinity space, or a real L infinity space. This is in this subset T is a subset of L infinity, whether or not L infinity is a real L infinity space or a complex L infinity space. So all of these arguments that I'm going to do are basically valid for both of them and apply for both of them. So both L infinity in the case of the reals and L infinity in the case of the complex are going to be inseparable. Okay, so here we have this set of sequences T, which is all sequences where the terms are either 0 or 1. And I shouldn't have put, well, that you could actually put that. Yes, it's an element of this set 0 with 0 and 1 in it. Okay, so if we take the distance, the d infinity distance, so this is obviously a subset of our L infinity, so it's a subset of our metric space. So now let's do some of our metric stuff on it. If we take the distance between x and y, where x and y are both elements of T, then what's it going to be? Well, if x and y are equal to one another, well, we can just use axiom 2 of metric spaces to say that it's going to be 0 if x and y are equal to each other, so if x is equal to y. But what about if they're not equal to each other? If they're not equal to each other, then that means that if I write these two sequences out, so let's do this for concreteness. So let's make up a sequence for concreteness. 0, 1, 0, 1, 1, 1, etc. And y is a different sequence. Now, at the very least, if it's a different sequence, one of these terms needs to be different from a term in here. So I could have it almost identical. It could be 0, 1, 0, 1, 1, and then we'd have to have at least one term different. So let's make this term the different one here. So it has to have one term different. So if I look at the distance between these two, distance between x and y, well, it was defined to be equal to the supremum of the modulus of xi minus yi over I is an element of the natural numbers. Well, xi minus yi at the only value xi minus y can take on is it can either take on 0 or it can take on 1, because xi can be 0 or 1 and yi can be 0 or 1. So the only distance, the only difference between those, the maximum difference between 0 and 1, these are the only two values that xi and yi can take on. So the modulus of the distance between them can only be 1 or 0. If you have, if you picked xi and y were both equal to 0, or what xi and y were both equal to 1, they'd obviously be 0. So this can only take on values of 0 or 1. Therefore, the supremum is going to take on values of 0 and 1. And it's going to take on values of 0 only when all of these, for all I as an element of the natural numbers, are equal to 0, which would imply that all the terms were exactly the same, i.e. this case up here where the two sequences are equal to one another. If a single term is out, then there will be one of these in this great big set. One of the terms, i.e. some I as an element of the natural numbers, one of these will have to be 1, and therefore the supremum of this set will be equal to 1. So it will be 1 if x is not equal to y. So if we restrict the metric just onto our set T, it forms a nice discrete metric space. Okay, great. But we know something about this. This set T is uncountable. We've proven that because it's because of this binary expansion argument. So that's suggesting something, that we might be able to do something here and show that it's not separable in the same way that we showed that uncountable discrete metric spaces were non-separable. So basically, let's suppose, now here comes the argument, let's suppose we had some set S which was countable, and was a subset of the L infinity metric space. So S is a subset of L infinity such that S is dense. Okay? Well, that would mean that for every single element, little x is an element of L infinity, then there needs to be an element of S. So let's say there must exist, so I'm going to put for all little x is an element of L infinity, there must exist a little s which is an element of big S, such that little s is an element of the ball, the open ball, or around X of size epsilon. So that's just the definition of it being dense. That every point in the L-infinity metric space is a limit point for this set S. This is also for all epsilon greater than 0. So for all epsilon greater than 0, you must be able to find a point in the set. Okay, so let me draw a picture. So if this is our metric space, L-infinity, with the infinity norm, not the infinity norm, the infinity metric on it, and you have a set S here, then basically you must be able to take any point X, and you must be able to put an open ball of any size around it, and you must be able to find some point of S within that ball. That's just the definition of S being dense within the metric space L-infinity. Okay, but now consider all the points of our set T. Consider T. If we consider the balls, if we consider, let's say, little t is an element of big T. So that's some sequence. Little t is some sequence of 0 and 1, 0, 1, 1, etc. So it's one of these sequences consisting of only terms 0 or 1. Okay. So if we take an element little t in there, and we consider the ball of around little t of size 1/2, basically all of these balls, if you consider all of these balls around every point little t is an element of big T, what I want to show you is if we draw T here and we have all of these points in T, so these are all the sequences of 0s or 1s, and we draw these open balls around these points of radius 1/2, then they cannot include any of the other points of T, is what I want to show you. Because for all other points, what should I call it? Let's say U is an element of T. The distance between little t and U we showed was going to equal 1, because we showed basically that the distance between any two points in the set T is either 0 if those two sequences are exactly the same, or it's 1 otherwise. So basically, if I draw an open ball around each sequence little t, which is an element of big T, which is just a sequence of 0 and 1s of radius 1/2, it can include no other sequence of 0 and 1s. It might include other elements of the metric space L-infinity. Don't get me wrong on that. It definitely will include other elements of the metric space L-infinity, but it won't include any other elements of the set T. So this only includes a single element of T. Only includes a single element of big T, single element of big T, and that is little t. It only includes the sequence of 0 and 1s that it's centered at. So basically, if I look at this set, this is the set big T, which I should draw inside L-infinity. So this is our subset of L-infinity. Oh dear, L-infinity. Oh dear, I've done it again. L-infinity. I keep wanting to write gamma rather than L. L-infinity. So it's a subset of L-infinity, and if I draw these open balls around the points of this set big T, then they are all disjoint. Basically, they don't contain any other elements of big T. What I want to say is that they do contain other elements of L-infinity. So they might contain other points that are in this part of the set here, and it's difficult to draw that. I should have them in here, but of course these balls are inside T. In the picture anyway. The picture's wrong, basically. There will be points that are in L-infinity but not in T, i.e. sequences that are in L-infinity that do not consist solely of 0 and 1s, which are within these open balls around sequences of 0 and 1s of radius 1/2. But these won't contain any other sequences of 0 and 1s within them, basically. So I have all of these sequences of 0 and 1s in T with open balls around them, which are disjoint. So if you have a set S, which is supposed to be dense within our metric space L-infinity, then that would mean it would have to have it would have to have a point in one of each of these balls, and these balls are all disjoint because a point cannot be in more than one of these balls, because that would violate the triangle inequality. So if I have, let's say, some little s in one of these balls of radius 1/2, so let's say little s is an element of the open ball around T of radius 1/2, that implies that little s cannot be an element of an open ball around some point T bar. So let's call this point T, and let's call another point over here T bar. It cannot be in that ball around T bar as well, of radius 1/2. The reason being that if it was, it would violate the triangle inequality. Because the distance between T and T bar is going to equal 1 because T is not equal to T bar, and we showed earlier that the distance between two sequences of 0 and 1 is either 0 if they're the same or 1 otherwise, and in this case they are not the same, so it's 1, but we could set you by the triangle inequality of the D infinity metric, the metric on L infinity, this is less than or equal to the distance between T and let's say S plus the distance between S and T bar. So if S was in both of these balls, then these distances would be less than 1/2, so we get that this distance was less than or equal to, well, in fact, yeah, well, if they were in these balls, this would be less than 1/2, and this would be less than 1/2, so we get that their addition was strictly less than 1. So by transitivity, we get that this distance was strictly less than 1, which would contradict up here. So basically, a point of the set S can only be in a single one of these balls. So you'd have to have, if S was going to be dense in the metric space L infinity, you'd have to have a point of S in each one of these balls. But there are uncountably many balls because there are uncountably many sequences little t in big T. So there are uncountably many sequences of 0 and 1s basically. So that is why you cannot possibly have a countable set which is dense within this L infinity metric space, because you need an uncountable many points to put in all of these disjoint balls around all these sequences of 0 and 1s basically. So the upshot of it all is that L infinity is not separable, and this argument works whether L infinity is viewed as a real or complex metric space. Oh, sorry, whether it's viewed as being sequences of real or complex numbers.